So far, I have shown you how to take into account the charges due to polarization, the polarization charges. And we saw those that we can take them into account by using two contributions, one a surface integral and one as a volume integral. Now, when when we have a physical situation, though, we have to remember we don't have just polarization charges. We also have charges, other ones that are, say, free to go anywhere. They may not be bound to their particular nuclei. And in those cases, we have to consider everything, polarization plus anything else that we have going on. So the way that I'm going to do this, I'm going to start by reminding you what is Gauss's law. In the integral form, I have the closed surface integral of E dot dA is equal to the charge enclosed over epsilon naught. Now, I want to remind you, the charge enclosed is everything. All charges enclosed by epsilon naught. Now, Gauss's law in the differential form is the divergence of the electric field is equal to the charge density over epsilon naught. Now, the charge density rho can be due to polarization or can be due to charges free to move anywhere. So I'm gonna start with equation 2 and I'm gonna say now, okay, let's say that the total charge density is equal to the bound charges due to polarization. So here, I'll show you, this will be due to polarization. So that's the charge density due to polarization. And this is the charge density due to everything else. And in the book, you will see it as that's the charge density of the free charges. Okay, but in one statement, this is due to polarization, and this is everything else. All right, and this is the total charge density that I need to use when I apply Gauss's law. Now, we know from the previous work on polarization that the charge density, the volume charge density of the bound charges is equal to minus the divergence of polarization. Now, I just want to indicate and make it clear, this is the uppercase, let's say this is the polarization charge density. We use rho, and this is the uppercase P. This is just polarization. And this is the dipole moment per unit volume. Okay, just to review. So I'm gonna try to make it clear. This is rho. This is the uppercase P. Okay, and this should also be rho, and this is also rho. All right, now what I'm gonna do, I'm gonna use this equation and I'm gonna plug it into here, and then I'm gonna take the whole thing and plug it there. So I will say that the total charge density is the one due to polarization plus the charges that are not, the charge density not due to polarization. And I will use this expression, let's call this equation 3. I'm gonna use 3 in equation 2. and I'm gonna multiply both sides with epsilon naught. So this times the divergence of the electric field is equal to minus the divergence of polarization plus the free charge density, and I'm gonna move this term to the left side, so this is rho sub f, and this becomes, okay, I'm gonna do dot product with epsilon naught times the electric field plus the polarization, and that should be equal to the free charge density. Now we define this quantity over here. This is what we define as the electric displacement d. So I can rewrite this as the divergence of d is equal to the free charge density. And I want you to pay attention now to this equation, this result, but also Gauss's law in the differential form. The divergence of E is the charge density over epsilon naught. In the integral form, I have the closed surface integral of E dot dA, Q enclosed over epsilon naught. Now, this reminds me of the differential form of Gauss's law, and I can rewrite this in an integral form. That will be the closed surface integral of d dot dA. It will be equal to the charges, not any charges. I have to use just the free charges. Now, because the charge density is not divided by epsilon naught, I don't need to divide with epsilon naught here. So this would be, let's call this equation 4. This is an important result, and this is the integral form of that important result. Let's call this equation 5. Now, I want to talk for a little bit about these results. When you are familiar already with applying Gauss's law in the integral form, you have found the closed surface integral and you have used it in different type of problems. I want you to pay attention to the fact that this integral form of Gauss's law is very, very similar to this integral form of electric displacement. So if you use not all charges enclosed, but just the ones that are the free charges, not due to polarization, then you can use Gauss's law, but you will find not the electric field, but the electric displacement d. Okay, so when we use Gauss's law in this case, just make sure that you're not finding E, but you're finding the electric displacement. And the same thing is true when you use a differential form. You need to be using only the free charges. Now, the reason why these two expressions 4 and 5 are important is because when you do an experiment, what you place or what you control are those charges that we call free charges. When you place them near other objects or inside materials, then polarization comes as a result of you using those free charges. So here, polarization is something that we cannot avoid. Once we use the free charges, at the same time, we will get the polarization of the material. So having on the left side something we control can be useful because I can control this. Okay, then that means I can calculate the electric displacement. And from electric displacement, if I have D, then I can use it to move on and hopefully solve for the electric field. Now I want you to remember the electric field is due to all charges. Okay, at the end of the day, it is possible that the quantity that I need is the electric field, and that is due to everything. So important to remember this. Neglect the ones with dark blue. All charges will give me the electric field. The free charges will give me just the electric displacement. Alright, and in problems we will see how to use Gauss's law and the free charges to obtain the electric displacement.